So we're going to finish up our discussion of routing protocols and talk about link state routing protocols. Now, unlike the distance vector routing protocols, link state protocols are newer, they're more complex, require more memory, more CPU resources on your routers and switches, and as a result, a lot of really old equipment or low-end equipment that you might see on consumer devices won't support any kind of link state routing protocols. Link state routing protocols are much more efficient at routing than distance vector protocols, but with that efficiency comes complexity. With RIP and other distance vector protocols, you just simply turn it on and have it start advertising routes, and it just kind of works. You probably saw that in the ICND1 course if you took that, and you'll see that when we talk about EIGRP here in just a little bit. However, link state protocols require a lot of router configuration, some more than others. OSPF is perhaps the most widely used and widely known, and once you learn all the ins and outs of how OSPF works, you'll see that it's a very efficient, very low overhead routing protocol. It's just getting over that initial hurdle. And we'll touch on some of OSPF here in the ICND2, but if you really want to get in depth with OSPF, I recommend taking the CCNP route course. So how do link state routing protocols work? Well, at the very basic level, link state protocols use link state advertisements to advertise routers and networks to one another. The router LSA advertises the router itself. It advertises all the interfaces, IP addresses, link state of all of the interfaces on the router, whether they're up or they're down. The link LSA is an advertisement for a subnet and all the routers on that subnet. Now, when a router starts up, the router floods router and link LSAs to all of the neighbors that are connected to it, which is generally all of the directly connected routers and switches if they meet the neighbor criteria. Those neighbors then forward those link state advertisements on to their neighbors in turn, and so on and so forth, until all the routers in the router domain have heard the link state advertisements from this newly brought up router. Now, that might seem a little bandwidth intensive, and it is in some cases. However, link state routing protocols ask the neighbor router, hey, I've got this particular LSA for this router or this link. Have you heard about it already from another source? And if the neighbor says, yes, I already know about that route, thank you very much, then the sending router says, oh, no problem. I'm here if you need me. That one mechanism right there is really responsible for preventing flooded LSAs and LSAs just looping over and over and over throughout the network. So that's what happens when a router starts up. Once all of the LSAs have flooded throughout the network, basically all the routers say, yes, I know about all of these routes, I know about everything on the network, then each router builds a copy of the link state database. It does this by running the Dijkstra shortest path first algorithm. That's a mathematical algorithm that, quite honestly, is too complex to put in this course because it just looks horrendous when you look at it. But honestly, unlike EIGRP, most people don't care about the math behind the SPF algorithm. They just care about what pops out the other end. Honestly, the SPF algorithm works kind of like a human being reading a map, trying to find the best path to a destination. And we all know the adage that the shortest route between 2 points is a straight line. However, if you think about a map that you might have, that's not always the case. For example, the shortest path between 2 points in your local city might go over a toll road or a two-lane road. And so I'm going to take this path that has more bandwidth, i.e. a 4-lane highway, as opposed to this dirt road through someone's cow pasture. And that's essentially what the SPF algorithm does. It considers the router that it's running on as point A and calculates all the paths to all of the networks that it knows about on the inner network, and then figures out which one of these is the best. Now, OSPF uses cumulative link cost, kind of like spanning tree, to be honest. Since the router knows about all of the routers and all of the links, and it has a map of the entire network in its memory, it can say, well, these networks are all connected by 100 megabit LAN links, and this other path, while it's fewer hops and it's shorter, it's 128K ISDN. And so I don't really want to take that route because I'm going to be waiting forever to go across the ISDN. I'm going to take this longer path around because in the long run, it's quicker. So once OSPF or any link state routing protocol computes all of these costs, the route with the lowest cost gets added to the routing table, obviously, because that's the best, shortest path between the 2 points. So now we have a functioning, stable network. We have all the routes learned by all the routers in the routing domain. And under normal operation, each router refloods all of its LSAs every 30 minutes. That's in case something happened and, hey, I didn't actually get to broadcast this LSA down because maybe the router exploded or some other reason why it couldn't broadcast it. It refloods everything every 30 minutes, just in case there were any undetected route changes or undetected link state changes. Obviously, you can go on the router and force the issue should you so desire, but you generally don't need to do that because OSPF's pretty good about keeping track of itself. So what happens when there's a failure? Well, obviously the router marks the link as failed. The router then floods this update LSA to every router on the network. It doesn't send the full LSA table, it just says, hey, this link to the 10110 network, it's failed. I don't have a route to it anymore, so you don't need to send your traffic to me. Once that LSA floods throughout the entire network, as it did when the router first started up, every router recalculates its local copy of the link state database to determine what routes actually need to change. The router says it's a slower link, I don't really want to use it, but as of right now, it is the lowest cost route to the destination network. Once it's done this, any changed routes are installed in the routing table, just like when the router first started up. Now, this process allows for much faster convergence times than distance vector protocols, simply because you don't have to wait that 30 seconds for the update, or you don't have to wait for the RIP routes to populate throughout all the routers on the network. Router A receives an LSA that says, hey, this link is down. It immediately floods it to all of its neighbors, and so on and so forth. So your convergence time is a lot less with link state routing protocols than with distance vector. And that concludes our overview of link state routing protocols.